Hello everybody, Namaskar. So now we will discuss the different component of the vapor compression refrigeration system. So I will discuss with the main component of the vapor compression system, that is the refrigerant. First of all, I will discuss the different refrigerant or variety of refrigerants. So in general, the refrigerant can be classified into two groups. One is the primary refrigerant, another is the secondary refrigerant. Primary refrigerant is basically the working fluids of the system which is going to the different component of the system and complete the cycle, and secondary refrigerant, that is basically the heat transfer fluid for the refrigerant. So some cases we are not using the evaporator directly for the cooling purpose, or evaporator is not directly connected with the heat source. So for that case we can use some circuit, so which is basically used to transfer heat from the heat source to the evaporator. So for that case some heat transfer fluid is used for that purpose, and that is basically called the secondary refrigerant. So now the primary refrigerant or the working fluid of the vapor compression cycle or any other refrigeration cycle, that can be classified into again two group. One is the pure refrigerant, that means the pure chemicals or pure working fluid. Another is the refrigerant mixture. So for this case the mixture of 2, 3 or more than 3 we can use as a mixture for the refrigeration purpose, or which is working as a working fluids. And then again the primary refrigerant, that can be the synthetic refrigerant, that means the man-made refrigerant, and that is the natural refrigerant which is already available in our environment. So synthetic refrigerant, that can be classified into four group. So one is the CFC, chlorofluorocarbon. So this chemicals or refrigerant consist of carbon, fluorine and chlorine. So this is also called the first generation refrigerant. Example is the R12 and R11. And then the second group, which is also called the second generation of refrigerant, that is the hydrochlorofluorocarbon. So this is consist of at least hydrogen, chlorine, fluorine and carbon. So example is the R22. Then the third generation refrigerant, which is called the hydrofluorocarbon. So this is consist of basically hydrogen atom, chlorine, fluorine atom and carbon atom. So example is the R134A, which is widely used in the mobile air conditioning system. So this is the third generation refrigerant. And then the new and fourth generation refrigerant, which is the HFO refrigerant. So this is the hydrofluoroolefin. So this is basically the unsaturated compound, and example is the R1234YF. So this is the one of the best substitute for the R134A, and this is used for the mobile air conditioning system, or we can use for the other air conditioning system. So this is the one of the best replacement for the R34A. Then the natural refrigerant, that may be the organic refrigerant or maybe the inorganic refrigerant. Inorganic refrigerant, this example is the ammonia, carbon dioxide, sulfur dioxide, water. And organic refrigerant, this is basically the organic compound, and this may be the saturated or unsaturated organic compound. So one example is the propane, isobutane. These are the organic refrigerant. And then refrigerant mixture. So refrigerant mixture can be classified into two groups. One is called the azeotropic mixture, another is called the geotropic mixture. So some mixture that can be behave like a pure refrigerant, that is called the azeotropic mixture, and other mixture of the refrigerant, that is called the geotropic mixture. Next, if we go for the history of a refrigerant, then this is the approximately the listed of some refrigerant which was used before 1930s, and this was introduced in that time, and approximately year of the introduction of this refrigerant that is given in this chart. So first one is the methyl ether. This was introduced in 1834. Then ether, that this was introduced in 1850 approximately. Then alcohol, this was introduced in 1856. Then dimethyl ether, this was introduced in 1864. Then ammonia, that was introduced in 1873. Then sulfur dioxide, this was introduced in 1875. Then the dimethyl chloride, this was introduced in 1878. Then carbon dioxide, this was introduced in 1886. Then the ethyl chloride, this was introduced in 1990 approximately. Then the isobutane, this was introduced approximately in 1920. So some of the important refrigerant and the introduction year, those are listed in this chart. Then 1930, the first generation of refrigerant was introduced, that is the CFC onwards. Then the second generation refrigerant, third generation refrigerant, then fourth generation refrigerant has been introduced as a refrigerant. So time to time the refrigerant use that has been changed. Okay, so now if we go to the properties of the different refrigerant, so if you see the pressure and temperature chart for the pure refrigerant, then because this chart is very important when we are selecting some refrigerant for certain applications in a vapor compression cycle. So if the pressure is lower than triple point pressure, so there will be the sublimation process, that means the conversion in between the solid to vapor or vapor to solid. So that we have already seen the lecture related to the solid carbon dioxide. So for the solid carbon dioxide, that pressure was basically lower than the critical triple point pressure. So there we have seen that there is a conversion in between the vapor to the solid carbon dioxide. So but for the other refrigerant or most of the refrigerant, basically we are interested in between the triple point pressure to the critical point pressures. So the subcritical cycle or subcritical vapor compression cycle, for that case this is the main criteria, that we have to maintain the evaporator pressure higher than the triple point pressure and the condenser pressure that is lower than the critical point pressure. So basically the pressure of the refrigeration system for a subcritical cycle, that pressure should be in between the triple point pressure to the critical point pressure. So in between that we will get the boiling in a evaporator and the condensation in a condenser. So and with respect to this, another point that is called the normal boiling point, that means what is the temperature or what is the melting what is the evaporation temperature corresponding to the normal ambient pressure, that is basically called the normal boiling point and normal boiling point temperature. So that temperature is very important, because we always prefer to use the refrigerant whose normal boiling point temperature is higher than the or that is lower than the evaporator temperature. That means the evaporator temperature you have to choose, that should be always higher than the normal boiling point temperature, so that the evaporator pressure should be higher than the normal ambient pressure. So there is any leakage from the outside air to the system, that can be avoided, so the system can be run more safely. So the conditions should be like that the evaporator temperature should be higher than the normal boiling point temperature and also higher than the triple point temperature. So then the above the critical point pressure, we can see that that line is basically called the pseudo critical line. So for that case we will see that there will be the conversion in between the vapor to liquid or liquid to vapor, but without any latent heat. Okay, so in the supercritical pressure, if you heated up any refrigerant, so that will be converted from the liquid to vapor without any latent heat of evaporation. Similarly, if you condense or if you that cool down any refrigerant, so that will be convert from the vapor to liquid without any latent heat of evaporation. So we have seen for the transcritical CO2 refrigeration cycle, that cycle the heat reaction pressure that is higher than the critical point pressure. So for that case there is a conversion in between liquid and vapor without any latent heat of evaporation. So if the refrigerant temperature is higher than the critical point temperature and higher than the pressure is higher than the critical point pressure, so that is basically called the subcritical fluid. Okay, so this figure is basically represent different phase zone of the refrigerant. So one is solid, other is liquid, other is vapor, and fourth one is the supercritical fluid. So now if we see the temperature entropy diagram for the different refrigerants, so we will see that the two type of behavior of the refrigerant that we can see. So the saturation line, the liquid saturation line for all the refrigerant, that is nearly same for all the refrigerants. So that slope of this line in a temperature entropy diagram is the positive slope. Okay, but there is a difference in term of the saturated vapor line. So for some refrigerant you will see that the slope of the saturated vapor line, that is just like a first figure. Okay, so where you will see that the slope of the saturated vapor line, this has a negative slope, but for the some refrigerant you may see that the slope of the saturated vapor line, this has also a positive slope within some temperature range. So this is just for the second figure. Okay, so in the first figure you will see that the saturated vapor line has a negative slope, and in the second figure we can see that the saturated vapor line has a positive slope. So the supercritical fluid region is similar for all the refrigerant. So there is only difference we can see in term of the slope of the saturated vapor line. So in case of the first figure, in this case, if the slope of the saturated vapor line is negative, so for this case, for the vapor zone, if you for any vapor zone, if you expand the fluid, then you will see that will be coming to in the two phase region. So that's why this type of fluid is called the wet fluid. But in case of second figure, for this case you will see that at high temperature at any point, let's say from this point, if you expand the fluid, then you will see that this expansion in a vapor zone. So that means the dry condition. So this type of fluid is called the dry fluid. Okay, so in case of wet fluid, if you expand the fluid at any saturation point, high temperature saturation point, then you will see that will be coming in the two phase zone. But in case of dry fluid, if you expand any fluid for high temperature saturation point like this point, then if you expand, then you will see that that is coming in a single phase only, that means the superheated vapor zone only. So this is the dry plate and first one is the wet plate, and some special cases if you see that the saturated vapor line is just like a vertical line, so that means that saturated vapor line is following basically the isentropic process. So that type of fluid is called the isentropic fluid. For example, if you consider the water, ammonia, so for this case the nature of saturated vapor line is just like a wet fluid. So that means the first case. So that means the ammonia is called the wet fluid. But if you consider isobutane, then you will see that for the isobutane, the nature of the saturated vapor line is just like the dry fluid condition. So for this case, if you use the isobutane and if you expand any saturation point, then we can see that that will be coming in a superheated zone. So that's why the ammonia is called the wet fluid and the isobutane is called the dry fluid. So what is the difference in terms of the processes that we can see in the next slide? So let's say if you draw the vapor compression cycle in case of ammonia and also in case of isobutane. So in case of ammonia and isobutane, both cases you will see that the expansion process, that means the outlet of the condenser, both cases that is the saturated liquid, and if you expand the process, so that expansion process is basically isenthalpic process. So after the expansion, that is coming in a two-phase zone for both the cases. But in case of ammonia, if you see the compression process, then you will see that the evaporator outlet, so evaporation process is the constant pressure process. So evaporator outlet is your saturation point, okay, saturated vapor point. So if you compress the saturated vapor or saturated ammonia vapor, then you will see that that is going to the superheated zone. Okay, because this is the condenser pressure. Condenser pressure is constant for the condenser. So condensation or the heat ejection process is basically the isobaric process. So here you will see that the compression process from the saturated condition to the superheated condition. So if you take the inlet condition of the compressor is the saturated vapor, then the outlet condition of the compressor should be the superheated vapor. But in case of dry fluid like the isobutane, then you will see that if you take the inlet condition as a saturated vapor, then after the compression, the outlet condition will become in a two-phase zone. Okay, so that's why if you want to get the outlet condition of the compressor, either the saturated vapor or superheated vapor, then the inlet condition of the compressor should be in superheated zone. Okay, so if you, for the idealistic case, if you assume that the either inlet condition or the outlet condition of the compressor should be the saturated vapor, then in case of ammonia, the inlet condition is saturated vapor but outlet condition is superheated vapor. But in case of isobutane, inlet condition is superheated vapor and outlet condition is saturated vapor. So to get the outlet condition saturated or superheated vapor, then we have to take some degree of superheat to maintain that outlet condition in case of dry fluid. Okay, so this is the difference in terms of the vapor compression cycle in between the wet fluid and dry fluid. Okay, then I am coming to the refrigerant mixture. So if we mix the two refrigerant, for example, so then you will see that that saturation curve that has the different at for inside the evaporation and inside of condensations, that will be the different temperature. So that means at constant pressure, if you heat the refrigerant mixture, then you will see that at some temperature the evaporation will start, but the end of evaporation, that means the evaporation process will end at some another temperature. So that means the start of evaporation and end of evaporation, both temperature will be different in case of refrigerant mixture. So we can draw the two-phase zone or the curve by this way. So in the first figure, we can see that this curve is drawn in between the temperature versus the composition. So let's say the composition of the two fluids, so fluid 1 and fluid 2. So let's say the composition of the first fluid is 100%, means that T1, that is the saturation temperature of the fluid 1, that is the saturation temperature for the fluid 1. Similarly, for the fluid 2, that means the fluid 2 is 100%. For that case, let's say the T2, this is the saturation temperature of the fluid 2. Then if you vary the composition in between the fluid 1 and fluid 2, then you will see that we will see the two different curve. One is called the boiling point curve, another is called the dew point curve. So boiling point curve means for any composition, if you heat the fluid, that fluid, or that means mixture, then you will see that the point where the boiling start. So that temperature is, if you locate, so that temperature is called the boiling point curve, that location of that temperature. Similarly, if you take the vapor mixture of two fluid, and if you cool down this vapor mixture, then you will see that at some temperature we will see the first liquid drop of that refrigerant. So that temperature is basically called the dew point temperature. So location of dew point temperature, that is also drawn in this figure. So then you will see that the location of boiling point temperature and location of the dew point temperature, that is different, that is given here. So similarly, if you draw the same thing with respect to the pressure and composition, then also P1 is basically the saturation pressure for the fluid 1 and P2 is the saturation pressure for the fluid 2, and any other composition you will see that the one is the dew point pressure, other is the bubble point pressure. Okay, so that means the upper portion above the bubble point pressure line, that is called the subcooled liquid, and lower side of the dew point pressure line, that is called the superheated vapor. Okay, so similarly in the first figure also, the lower side of the bubble point temperature line, that is called the subcooled liquid, and above than the dew point curve, that is called the superheated vapor. So for both the cases, we can see that either we can maintain the constant pressure, then we will see that the boiling dew point and the boiling point are different. That means the dew point temperature and boiling point are temperature different for the same pressure. Or in the second curve, we can see that for any composition, for the same temperature, we will see that a different dew point pressure and different bubble point pressure. So the Reynolds law of partial pressure, that is applicable for the vapor phase, and Dalton's law of partial pressure, that is used for the vapor phase, and Reynolds law of partial pressure, that is applicable for the liquid phase. So if these two laws are applicable, or that is the true for the both for the vapor phase and liquid phase, then that type of mixture is called the ideal mixture. And if these two laws are not valid, in that case, that is called the non-ideal mixture. So then one interesting thing we can see in case of the refrigerant mixture. So we have seen that in general that the dew point curve and boiling point curve are different for the refrigerant mixture, but some of the composition or certain composition of a refrigerant mixture, that composition or that mixture may be the mixture of two refrigerant or mixture of more than two refrigerant, then at the sum composition you can see that the dew point curve and bubble point curve is basically merged as a single point. Okay. So that means at this composition the start of boiling and end of boiling occurs at basically at the same temperature. Okay, if you maintain the constant pressure. So that means that at that composition that refrigerant mixture can behave as a pure refrigerant. So then another two type of difference we can see for the different mixture or different so some cases we can see that single point or that optimum ratio where we will get the same dew point and boiling point, so that may be the lower than both the boiling point of the individual refrigerant. Okay, so that is called the minimum boiling point azeotrope or azeotropic mixture, and some cases you will see that the optimum boiling point or that boiling point at the optimum composition, that is basically higher than both the boiling point of the individual refrigerant. So that type of optimum refrigerant mixture, that is called the maximum boiling azeotropic mixture or maximum boiling azeotrope. Okay, so that means in case of azeotropic refrigerant mixture, that boiling point temperature can be higher than both the boiling point of the individual refrigerant, or that may be lower than both the boiling point of the individual refrigerant, or maybe in between the two boiling point of the two individual refrigerant, whatever may be. So that may be vary, that may be either minimum value or maybe the maximum value. So but that boiling point, that means the dew point and boiling point will be same at that composition. So at that composition that refrigerant behave like a ideal or pure refrigerant. Okay, so that is called the azeotropic mixture. So now we can just differentiate in between the azeotropic mixture and geotropic mixture. So azeotropic mixture, that means that and that optimum composition that will behave like a ideal pure refrigerant. So in the first figure you can see that T temperature entropy diagram. So that behavior or at the constant pressure, the constant pressure line will be same as a pure refrigerant. Okay, but in case of geotropic mixture, so for this case you will see that the constant pressure line is different as compared to the pure refrigerant. So that if you see from, so that means if you heated up any refrigerant, any geotropic mixture, then you will see that the start of boiling that is occurring at some temperature and end of boiling that is occurring at the higher temperature. Okay, so similarly we can also see the difference in the pressure and enthalpy plot for the azeotropic mixture and geotropic mixture. So azeotropic mixture is basically just like a pure refrigerant. So you can see that this is behave that constant isothermal line, constant temperature line is just like a behavior of a or isothermal line of a pure refrigerant. But in case of geotropic mixture you will see that the isothermal line is just different. So you can see that the temperature is constant but pressure is variable. Okay, so that means for the geotropic mixture, if you maintain the constant pressure, then the temperature will be different at the inlet, at the start of boiling and end of boiling. Similarly, if the temperature is, if you want to maintain constant, then you will see that the start of boiling and end of boiling your pressure is different. Okay, so here in the second figure you can see that if you maintain the constant temperature lines, then you will see that from the liquid this will start vaporizing or start of evaporation at some pressure, and then during this two phase region or during that evaporation process you will see that constantly the pressure is decreasing at the constant temperature, and then at the end of boiling that pressure is the basically lower than the pressure of the start boiling start. Okay, so there is a variable pressure process in case of boiling. Thank you.